I want to take just a few minutes to sell you on the idea of flashcards once again. The beauty or the power of flashcards is if you have several pieces of information that you need to know for an exam. This is not true just for calculus, but for biology, for anything that is, vast amounts of information that you're responsible for on an exam. If you have, let's say, 50 flashcards, and you go through them and you know 30 of the flashcards, you know the information on them, front and back, you're really comfortable with that, then you get to put those 30 flashcards aside and you have a really efficient way to spend your study time on just the 20 flashcards that you need to make sure that you understand. When you put something like this table in your notes, and there's more to this table if you're going to do that, there are 9 tests altogether that need to be in your table. If you put a table like this in your notes, every time you look at this table, you're looking at all 9 tests. It doesn't get highlighted to you that you might really be struggling with 2 out of those 9 tests. And so when you look at it, you think, yeah, I have most of that down. I understand 7 of the 9 tests. Or you may not even realize that you don't understand all of them, you just understand most of them. So this is, to me, an excellent illustration of where flashcards would really, really make the difference and definitely make your study time as efficient as it needs to be. So here's a summary of all the tests that we're going to use for our series. These are not in the order that I taught them. I borrowed this off the internet. Let's hope it's okay. We'll talk about the name of the test and what the series nth term will in general look like, what this particular test tells you about convergence, or what this particular test tells you about divergence, and then if there's any other information that this test tells you about your series, it's over there in the comment column. So let's start talking about the nth term test for divergence. This is the nth term test for divergence. And I like writing the whole name because it tells you right there, I'm only testing for divergence. This is for any positive series. So for any positive series, the nth term test for divergence tells us that if we put that nth term into the limit as n approaches infinity and we get anything other than 0, any real number value that is not 0, then we're guaranteed that series diverges. This test tells you nothing, absolutely nothing about convergence. You will never run the nth term test for divergence and state that your answer is the series converges by the nth term test for divergence. This test doesn't test for convergence, it only tests for divergence. So make sure that you're really comfortable with that. Now, geometric series, the power to geometric series, or the secret or whatever, is recognizing the form of the nth term. You want to look at the form of the nth term. That's really important because it needs to be of the form a times r to the n minus 1 when n starts at 1. Notice here this form is n equals 0. So you might actually want to put this on your flashcard or in your notes. Start at n equal 1 up to infinity, because this form is going to allow you to find the sum. This form will allow you to run or recognize that we have a geometric series, will allow you to find r, your common ratio, but if it also asks you to find the sum of that series, you're going to have to put it in the right form. So all we need to do here is recognize the common ratio. And based on the value of the common ratio, this tells us not only about convergence, but it tells us about divergence as well. Anytime the absolute value of your common ratio is less than 1, that geometric series converges. Anytime it's anything larger than that or equal to 1, this geometric series will diverge. For a convergent geometric series that actually has a sum, you can find the sum by identifying A and R and plugging it into this formula. Next is collapsing series. Collapsing series, also called telescoping series, for those of you that Google things and want more information. But a collapsing series usually can be identified as a fraction minus a fraction. Now, you may have to do partial fraction decomp to get it in that form, but if you have something that is a fraction minus a fraction, you're probably looking at a collapsing series. If you will generate enough terms to see the pattern for cancellation, you can determine whether it converges or not. If it does converge, it's the second of two types of series where we can actually find what the overall or final sum is. And so we want to generate enough terms to see the pattern for cancellation, cancel all the terms that are going to collapse, and then what is remaining we plug into that limit as n approaches infinity. And the result of that limit will be the sum of the collapsing series. Notice what it says about divergence. Nothing. Nothing. Collapsing series should converge. If you are doing work on a series that you think is a collapsing series and it's not behaving for you, where things are disappearing and collapsing, where you can find that nth term to put in the limit to find the sum, you're probably not dealing with a collapsing series. Next, one of our favorite types of series is a p-series. The secret to a p-series, just like geometric series, is recognizing the form. The form is 1 over n to the p. If p is greater than 1, we're guaranteed that p-series will converge. If p is less than or equal to 1, we're guaranteed it will diverge. We know nothing about the sum of a p-series. Alternating series. Alternating series are of a form where they have an alternating term. The alternating term is multiplied by what we're comfortable with calling the positive counterpart or portion to the alternating term. If we have this condition, convergence for an alternating series is an if-then statement. If the terms in our series are getting smaller as we generate the next term in the series, if it's getting smaller and we don't care about the positive and the negative, then we can run the limit as n approaches infinity on the positive portion of the nth term, just the positive portion. And if we get 0, we're guaranteed that alternating series is converging. We also know that the error bound for any alternating series is just the next term in the series. And we saw that just a few lessons ago. So there's the first 5 tests. Here are the last 4 tests. The integral test has an if as well. If my nth term acts like a function where that function is continuous, positive, and decreasing, then I can run this improper integral, and as the improper integral behaves, so does my series. So does the sum of all those terms. If the function that is acting like the nth term in my series converges to a value inside this interval, then the series sum will converge as well. If the area in the plane doesn't converge, if it diverges, then the series sum will diverge as well. All right? We didn't really talk about the remainder, and I don't want you to worry about having that in your notes. That basically is just saying we're not guaranteed that the sum and the function will converge to the same value, but we are guaranteed that the error will be relatively small and will lie in between, all that kind of stuff. We don't really need to know that. All right, the next test, the most powerful test. The test we're going to run most often, the test I need for you to know inside and out, and that's the absolute ratio test. If we are given a positive or an alternating, either one, the power of this test is that it works on both because of the absolute value. If we have a series of any kind, we can find the n plus first term, we can plug it into this limit as n approaches infinity, and we get rho. If rho is less than 1, that series converges. If it is an alternating series, it converges absolutely. If we get any value greater than 1 out of the absolute value of that ratio, that series diverges. If we get equals 1, the test fails, and we have to find another test. This one is really powerful for any kind of exponential function, not function, but nth term, any kind of factorial. Remember, it stinks for a polynomial over a polynomial. I'm not saying it always fails, but if it's going to fail, that's where it's most likely to fail. The direct comparison test for us, unless we're told to, is more than likely a test of last resort. If all else fails, the direct comparison test just won't fail. The secret is in finding the relationship between the a sub n that you were given and the b sub n that you have to come up with. And you have to recognize what you're after. What you're after here is you want b sub n to be greater than a convergent series if b sub n converges, or you want b sub n to be less than a divergent series if b sub n diverges, because then anything greater than it must diverge as well. So the secret is in choosing the correct b sub n and knowing what the results are going to give you. The limit comparison test is probably our second most powerful test. The limit comparison test is great for series that act like a polynomial over a polynomial. Where the absolute ratio test fails us, the limit comparison test gives us a great result. Again, the secret is in knowing what b sub n does and in recognizing what that result means. All right, so make sure that gets put into your notes. Notice this is for positive test only and positive test only. The integral test also is a positive series test only. So that's it. There's all your tests. Come to class next time and we'll do some mixed review.